Alright, so in this video I'm going to show you some more complicated empirical formula problems. So oftentimes they're not just going to give you the mass or the percentage of the elements in the compound, they'll give you lab data. So there are three typical situations where they'll give you lab data and then you have to find an empirical or molecular formula. So anytime that we're trying to get an empirical formula, you have to get the ratio of moles for each element or component in the compound. So if you're given lab data, look at it. How can I determine the mass or the number of moles of each of the elements or components in this compound? Because that's ultimately what you need to get. As soon as you get that, then it looks like every other empirical formula problem that we've had. So one of the first examples is lab data with an oxide. So you have some sort of metal and it reacts with oxygen gas. So typically what happens is you'll heat it and then it'll react with the oxygen gas that's in the air and you get the metal oxide. Well, again, if we have a metal oxide, what we need to do is we need to determine the amount of the metal and then the amount of the oxygen. And then after that, then it's like every other thing that we've ever done. So we have the mass of the crucible, the mass of the metal with the crucible, so that's after I put in just the metal. Then I heat it up, and then the mass, well, it does go up. That's because we're adding oxygen to that metal. It's reacting, and then they heat it up again, and then they heat it up again. So the reason that they keep heating is they want to ensure that they've reacted all the metal out, because when you go and you take the mass of this crucible, the scale is not going to discern between the metal and the metal oxide. So you have to make sure that you've reacted out all the metal. And the way that you do this is that you keep heating it until the mass just stays the same. That means that you've reacted everything out. So you need to get two things here. You want to get the mass of the metal. And then I also need to get the mass of the oxygen. Once I do that, then it's like everything else I've ever done. So the mass of the crucible, and then I have the mass of the crucible with just the metal. So if I subtract these first two values, I'll get the mass of the metal by itself. So that's going to give me 2.241 grams of nickel, because it did tell me what it was up here. All right, so now then I went and then I heated up the crucible and the metal, did it again. So now this is the mass of the metal oxide plus the crucible. So you can actually get the mass of the oxygen a couple of different ways, but I know this mass is higher because I've added oxygen. So if I take the difference between the mass of the metal and the crucible and then the new mass, I should get the mass of the oxygen that I've added. And that gives me 0.611 grams of oxygen. Okay, so at this point it looks like everything else. I've got the mass of each of my elements. So the next step is to go to moles, divide by small, multiply till whole. So convert to moles. 1 mole of nickel weighs about 58. That's going to give me 0.03818. All right, so do the same thing for the oxygen. That gives me 0.03818, same thing. So now divide by small. And we get 1 and 1. So my empirical formula is just NiO. All right, so when we do a problem like this with oxide, get the mass of the metal by itself, get the mass of the metal oxide by itself, and once you get those things, then you can subtract the metal from the metal oxide, or you can actually get the oxygen by itself a couple of different ways looking at your data. But the main thing is you want to get the mass of the metal, you want to get the mass of the oxygen by itself. After that, it's a typical problem. All right, so we will also see problems with hydrates. So with hydrates, you're going to see a compound that's surrounded by water molecules. So you might see something like this: copper sulfate, pentahydrate. And what this means is that the copper sulfate is surrounded by 5 water molecules. So if you're looking for an empirical formula of the hydrate, typically you're actually going to be looking for the amount of the salt, so whatever the ionic compound is, and then the amount of the water. So you're not going to be looking at individual elements here, you're going to be looking at 2 components. The anhydrous salt, okay, that's the ionic compound, and then you're also going to be looking for the water. So typically when we're looking for the formula of a hydrate, what we're going to do is we're going to heat it, because if we heat it, the water will evaporate and then we'll be left with the salt. So that's the kind of data that you'll have. You'll have a mass of the whole hydrate, it'll be heated up, and then the mass should go down because the water is going to evaporate. So in this problem, we have a 15.67 gram sample of a hydrate magnesium carbonate was heated without decomposing. The carbonate, so they heated up, drive out the water. The mass was reduced to 7.58 grams. So the mass originally was 15.67 grams. That's the total mass. That's the mass of the entire hydrate. And then after we heat it, it goes down. So it goes down to 7.58 grams. So this should just be the salt by itself. So the magnesium carbonate. So we're going to get 2 things. We're going to get the mass of the salt, and then we need the mass of the water. So the mass of the salt is just going to be 7.58, because what you have left over should be your salt. And then your water, well, if the whole hydrate is 15.67 grams, if the whole hydrate is 15.67 grams and the new mass is 7.58, you just take the difference, and that should be the water by itself. So that's going to give me 8.09 grams. All right, so now I have the mass by itself. So instead of looking at each individual element, I'm looking at the compound and then the water. So at this point, it's still, I've got mass to moles, so now I'm going to get the moles of the salt and get the moles of the water, and then divide by small, and then it's typical problem at this point. So 7.58 grams of magnesium carbonate, convert that to moles. So 1 mole is equal to 84.3 grams. And then we have our water, which is 8.09. So we get 0.0899 here, and then for our water we get 0.4494. All right, so now divide by small. So this is approximately 1, and this is approximately 5. So the way that we write this, well, it's magnesium carbonate, dot, and then 5 H2Os. All right, last thing. We have a combustion problem. This is one of the more complicated problems. So when we have a combustion problem, typically what you're going to be looking at is some sort of hydrocarbon. Okay? And what they do is they actually react it to oxygen gas, and then they collect the products of CO2 and water afterwards. Well, when they do that, they know that the hydrocarbon, which contains mostly carbon and hydrogen, the carbon and the carbon dioxide comes from this, and then the hydrogen and the water comes from the hydrocarbon as well. The oxygen is a little bit different because you it could have oxygen in the hydrocarbon. So alcohols have oxygen as well, but you've also got oxygen being reacted. So we can look for the amount of carbon in the carbon dioxide that we collect, and we can look for the amount of the hydrogen in the water that we collect at the end. So in order to do this, we still need to get the mass of the carbon by itself, and we need to get the mass of the hydrogen by itself. The tricky thing is that you're going to have CO2 and you're going to have water here. So you have to use a percentage, because I know for carbon dioxide, the mass of carbon dioxide is 44. Well, the mass of one carbon is 12. So 12 divided by 44 is about 27%. So if I was given an amount of carbon dioxide and I want to know how much carbon is in that, I can use the percent. Well, how much is 27% of the amount of carbon dioxide that you have? So we're going to be using percentages with combustion problems. So we get the amount of carbon using the percent of carbon and carbon dioxide, and we get the amount of hydrogen from the percent of hydrogen and water. All right, so let's do that first. So we have the mass of carbon. Well, complete combustion of a 0.255 grams of an alcohol. Okay, so that means that we also have oxygen in there too. Produces 0.561 grams of carbon dioxide. And then when I look, I was also given the mass of water. Okay, and that's 0.306. So I know the carbon and the carbon dioxide has to come from the hydrocarbon, and I know the hydrogen and the water has to come from the hydrocarbon. So what I'm going to do is I'm going to multiply the amount of carbon dioxide by the percent of carbon in the carbon dioxide. So that's about 27%. So of this 0.561 grams, how much of it is just carbon? So you get 0.1529 grams of carbon. Okay, so now I've gotten the carbon by itself. Now I'm going to do the same thing for the hydrogen. So I know that in water weighs 18 grams. The hydrogen is 2 grams. So that's roughly 11%. So of this 0.306 grams, how much of it is just hydrogen? And that's going to give me 0.033. Okay, so now I've got my mass of my carbon, I've got my mass of my hydrogen, but because this is an alcohol, they will not always have oxygen, but in this case, since it's an alcohol, I do also have oxygen. Remember, I can't look at the percentages here because I've also got oxygen being reacted. So what I have to do is I have to say, okay, the total mass of the entire hydrocarbon is 0.255. So I know that 0.1529 grams is carbon and 0.033 grams is hydrogen. Well, just take the difference. So take the amount of carbon, add that to the amount of hydrogen, and then subtract that from the total, and that will give you 0.06811 grams. Okay, so now I've got my amount of carbon, my amount of hydrogen and oxygen. Now it looks like a typical problem. So now I can go through, get my moles, divide by small, multiply till whole. Okay, so for carbon, we have 0.1529 grams. For our hydrogen, we have 0.03399 grams. And then for our oxygen, we have 0.06811. All right, now convert to moles. That's 0.01274. Do the same thing for the hydrogen. And then do the same thing for the oxygen. Yeah, 0.00425. All right, now divide by small. So we're going to divide by 0.004 for everything. That's going to give me 1. That's going to give me approximately 8. And this is going to give me approximately 3. So my formula is going to be this. Or you could also write it like this, although this is not expected. All right, so for combustion, what you're going to do is you're going to calculate the percent of carbon and carbon dioxide. You're going to multiply that percentage as a decimal to the amount of carbon dioxide. That gives you the mass of carbon by itself. Do the same thing for the hydrogen. Okay, if it's an alcohol, which they will not always be alcohols, you're going to get the mass of the oxygen by subtracting the mass of, carbon and hydrogen from the total mass of the compound.